So for this next example, it's a very, very similar in concept to the example that we kind of worked towards the end yesterday. I think what you guys are going to find, it's a little bit less intimidating today than it was yesterday because you've done it a couple of times. Okay? So, you know what? I'm going to shut up for a second, other than to tell you, and let you guys read this, other than to tell you there was a typo, and both of these are supposed to be 743, not 543. Okay? All right, so the first thing I'm going to point out is, like, eventually what we're being asked to do is instruct and interpret a 95% confidence interval for a proportion. And that's literally all stated for you in terms of what you're going to do. So from there, you would say, what's the name of the procedure that would help me construct this kind of interval? The name of that procedure is a one sample Z interval for P. And we would say, well, what does P stand for? The true proportion of residents who will vote for this candidate. And you guys, do we have an estimate for the proportion of people who will vote for this candidate? Any estimate? Well, it's close, except for we're not trying to estimate the number of people who are going to vote. It's the proportion, right? So that 476 on its own isn't like, right? Okay, so, but our best estimate is in fact P hat, which is 476 out of 743.
Is there a reason, well, there obviously is something, like, why do you not test, like, random and normal and all that?
Relax.
Well, no, I'm just wondering.
Yes, all will reveal itself in about a minute.
Okay. Well, I'm just wondering.
I want to, like, I'm trying to emphasize a reasoning approach here that to make sure you understand why we do what we do. Okay? Okay. Is everybody good? Hey, what are we getting for this? 0.64. Cool. Okay, you guys. So our estimate, if we're trying to estimate who's going to vote for this candidate, right now our best guess is 64%. Now, should this person feel confident? You feel like it's a toss-up?
Yeah.
Why?
Because it might not be accurate.
Oh, wait. Why? Why might this not be
Because
accurate?
the samples aren't perfect.
Because this is a sample and samples aren't perfect. So because I know that samples aren't perfect, maybe what I want to do is give myself a little bit of wiggle room, like, I don't know, a margin of error. But before I'm allowed to do that, I got to make sure I'm allowed to give myself that margin of error. Everybody good? And to make sure I'm allowed to give myself that margin of error, I need to check 3 basic assumptions. Everybody good? What's the first of those basic assumptions?
Random.
And by the way, is that condition met?
Yes.
We were in fact given that this was a random sample. Okay, next. And you guys, as soon as we have that's a random sample, what that basically says is, hey, this 64% is probably representative. It's an unbiased estimator. Now that we know we have an unbiased estimator, the next thing we want to do is be able to use Z-star. In order to be able to use Z-star to build that margin of error, we need the normal condition to be met. Because use the normal condition to find Z-star. Is the normal condition met here, and how do I check it?
If n times p hat and n equals 3,
All right. So we're going to do 743 times 0.64. We're going to do 743 times 0.36. What are we getting? We should get 476-ish. And then 267. Cool. Cool. Are we feeling okay? Lastly, did I give you guys a visual representation of this 10% condition yesterday? Or did I not think of it until the afternoon? Because I have a good visual representation of... Would you guys like to see a visual representation of it?
Yeah.
Okay. Did I tell you guys, instead of naming puppies X bar and P hat, I need to get a second air plant, but my little air plant here, this is P hat. That's what I named it. Little P hat. Let's hope I don't kill it, as I do most of my plants. Okay.
They're pretty hard to kill.
I have killed an air plant, so
Oh.
while they are challenging to kill, I would like you to give me the credit I deserve. Yeah. Okay. So, you guys, in here I have a jar full of marbles, right? Okay, if I give little P hat a rest. Okay, and in this jar full of marbles, there's some red, right? And I could say, I'm going to take a random sample of, I don't know, 3. Red? Yes?
Mhm.
Did the probability of red change?
Yes.
Yeah.
Did it change by a decent chunk?
Yeah.
Yes. Cool. You think it'll roll away? Here. I'm going to grab one. Red. Did the probability of red change in this one?
Not really.
It changed. It still changed. It still changed. Neither of these is independent because the probability did change the minute I pulled this out. But when I pulled the red out of that one, it changed a decent chunk. When I pulled the red out of this one, not so much. Is that, you guys catch my drift now? Okay, and so this whole idea of sampling without replacement is not independent. But why, how come here was fine, we're still comfortable saying it didn't really change, but over there, it did change. Why?
The 10%.
Yeah.
The size of the sample relative to the population. Okay. Does that kind of help you visualize that 10% rule? Like in this one, we don't care. But if I took, I don't know, don't spill. All of these out, now my proportion of red might have changed a little bit, right? Because I took such a bigger proportion of my population. Is this cool? Okay. So. What? Nothing. So. Here you go, P-Hack. Here's your sunlight.
I like your window shelves.
Yeah, I just, they
Are
need.
they staying on?
They fell first. Well, at first I had them. There's these little like spacer pieces on them, and so when I tried to center them, that caused a problem because the framing pops out a little bit and it was putting too much out. And then I think I just gotta stop touching things on them and then it'll last a little bit longer. So remember we said as long as my sample isn't too big relative to the size of my population, that change isn't gonna be enough. Okay, so in this case, my sample size is 743. We're just gonna go ahead and assume it's less than 10% of residents. How are we feeling so far? Right on? So, okay, so the thought process is, we got this sample, we know it's probably close but not right, so we're going to give ourselves that margin of error, right? We just said, hey, we're allowed to do this. Now what? Silly thing, we do it. Yeah? We just gave ourselves permission. Let's work it through. So, we said, what was my best estimate? P hat, my 0.64. We know it's not right, so we give ourselves the wiggle room, the plus or minus. Okay? How do we do the margin of error? A critical value times a standard deviation. Since we're doing a z-interval, z star is our critical value. And what z star is appropriate for a 95% confidence interval? 1.96 times. You guys, what do you guys think my standard deviation is going to be? P hat. Look at you. This is where you guys become smarter than me, so I'm going to let you guys type this in for me. What are we getting? Yes. Think of like in Algebra 2 and pre-calc where you did that interval notation that went from least to greatest. It's the same. It's the same notation. Yeah. Are we feeling okay still? Is this feeling better than it did yesterday? Didn't I tell you, like the first day feels terrible and then it gets a little bit better and you get used to the process. Okay, hold on. And then, man, we've done so much. We just have to do one more thing. We have to make our conclusion. But before we make our conclusion, I want to go back to when we estimated Mr. Wyans' age, right before Miss Lombardi ruined it for everybody. Right? Okay? What did it, we ended up with an interval, yes? What did it mean if our interval was right? Air quotes. That the actual value we were trying to estimate is somewhere in the interval. So if I look at this here, here's my interval, right? What is the value I'm trying to estimate? Thank God I told myself what the value I was trying to estimate is. This P. Is everybody good? And how confident can we be in our answer? 95%. 95%. So we are going to say we are 95% confident that the interval from 0.6 to 0.67 captures whatever you want to say, and you're just going to throw that P back in there. The true proportion of residents who will vote for the candidate. All right. We're going to go back. We're going to talk about Mr. Wyan one more time. How did you feel about your answer plus or minus? Compare your feeling confidence in plus or minus 2 years versus plus or minus 5 years.
Confidence was higher, it was a larger margin.
Larger confidence equals larger margin of error. Are we comfortable with that idea? Okay. So if I went through and I said, all right, what if instead of doing a 95% confidence interval, I'm doing a 90% confidence interval? The interval would be narrower. Yes? Mathematically, why does that happen? What would change in my formula for the interval?
Z-star.
Z-star, and what would it become?
1.6.
1.6. So I'm going from 1.96 to that 1.645. That Z-star gets smaller, which means my margin of error is getting smaller. And if my margin of error is smaller, overall, the interval gets narrower. We doing good? All right, so if I were to ask you what are the two components of the margin of error, what would you tell me? There's two things that make my margin of error.
Z-star.
My critical value and
Standard.
the standard error. All right. Which of these things in this formula do we have control over? Z-star. So we can pick our level of confidence, sort of. But as we say that, you really don't. Like, first of all, we only use 90, 95, 99%. And usually if you're a statistician who's being like hired out to do something, like to create these estimates, usually someone tells you which level of confidence they want you to use. Okay? All right. What else do we have control over? N. We can pick our sample size. So the two things I can do in advance to manipulate my margin of errors are my level of confidence and my sample size. Those are the two things I can choose that influence how wide my margin of error is going to end up being. Okay? All right. Now, I want to talk about confidence a whole lot more. Okay? So there's two things I'm going to be asking you when it comes to these confidence intervals. There's two things I can ask you to interpret. One of them is the interval, and one of them is the confidence level. So if I ask you to interpret the interval, I'm asking, what do the 60 and the 67% mean? This is how you interpret it. This is what that means, okay? If I to interpret the confidence level, I'm asking, what does the 95% mean? Is everybody with me so far? And this is something that is a really, really challenging topic to understand. So I'm going to go back to a visual that we used the other day. Let's go ahead and say I'm interpreting the confidence level for this candidate above. Okay. To interpret the level of the 95%, I might say something like, if we take a large number of samples, we can expect 95% of the resulting intervals to contain the true proportion of residents who will vote for the candidate. In the multiple choice, they love to ask questions interpreting confidence levels. And they always put one saying the probability that the actual proportions between these two numbers is 95%. The answer to that is never the answer, and it's always the one that gets put. Okay, so don't be that guy. All right, so in actual practice of doing statistics, what happens is what you have the person hiring you to create this confidence interval to make this estimate for you and for them. And what they usually do is they say, hey, I want to be 95% confident and I want to be within 3%. Is everybody with me so far? And so if that's the case, well, then I no longer have control over the Z-star. How do I ensure that my margin of error is within 3%? There's only one other thing I can control. My sample size. So this last question, and then we'll be done for today, and I'll give you guys, did I give you guys the review yet? Yeah. Okay. And I'll let you guys work on that review. The last question we're going to focus on is how do I determine what size sample I should take if I want to be 95% confident and I want this to be my margin of error. Okay? So it goes kind of like this. We just said the margin of error is the Z-star times the square root of p hat, 1 minus p hat over n. So if I tell you I want my margin of error to be within 3%, are you guys comfortable with saying that within 3% means that this value has to be less than or equal to 0.03? Is this okay? And if I said, hey, I want my margin to be within 5%, we would use 0.05. And if I said I want my margin to be within 7%, it would be 0.07. Okay? And as I go to answer this question, what should my variable be? What am I trying to find? My sample size. If I say what size sample, the n should still be part of my equation, yes? Okay? And then 95% confident, so everything else we need to fill something in for. Okay? What should I fill in for Z star to be 95% confident? $1.96. What about for p hat and 1 minus p hat? because keep in mind, we would do this before we've taken our sample, because we don't know what size sample to take. Do you guys catch my drift on that? Okay, so what should I use? What value for p hat would have the most uncertainty? Remember, standard deviation is about uncertainty, yes? Okay, so I'm going to use the most uncertain I have because that's the widest my possible, no matter what happens in my sample, it's the widest it could be. What value for p hat suggests the most uncertainty about what will happen? Guys, if I pick out of that bin, would you guys feel pretty confident you could guess what I'm going to pick out of it? Why? Because it's mostly one color. Okay? Even if I had two colors in there, how could you make it so you'd be the least confident about what I would get out of it? Make them even. 50-50 is my most uncertain. Cool? So when we're trying to find a sample size to minimize our margin of error, we use 0.5, and then 1 minus 0.5 is another 0.5. We use p hat equaling 0.5 to find sample size. All right, once we get to this, while icky, are you guys with me that this is just an inequality we can solve? And if I asked you to solve this inequality, what would your first step be?
Subtract 1.96. Divide.
Divide 1.96. I'm going to start with, let's get rid of that 1.96. I get rid of it by dividing, yeah? I'm going to kind of put this up here again. You guys, I don't know what 0.03 divided by 1.96 is. I know it's really... 0.0153 and some change. Y'all, as we go through this, you will not clear out your calculator. You're always going to try to use the decimals from the problem before. Is it? You guys with me on that? Okay. What should I do next? Square both sides. Okay. Would you guys also be okay if I do 0.5 times 0.5? So I'd get 0.25 over n is less than or equal to, and you just get this really tiny decimal. In fact, your calculator is going to give that to you in scientific notation.
Can we write it on our paper in scientific notation or no?
Yeah, you can be fine with that. Then what would you do? Multiply by the denominator. Are you guys with me that really that just means that 0.25 over the 0.000234 has to be less than or equal to n? And guys, when I did this, I got 1067.11 has to be less than or equal to n. And for the sake of what I'm going to show you in about 2 seconds, I'm going to rewrite that as n has to be more than 1067.11. Hold on. What is n supposed to represent? What does n stand for? Sample size. You guys, are you going to go out and ask 1067.11 people? So what should n be?
To round up.
You have to round up. Why do I have to round up? Because I said my sample size has to be bigger than this. Yes? So, a few years ago, there was a sample size question on the AP exam, and a whole bunch of kids left it as 1,067.1, and they got a P instead of an E. And the way that shook out was there was another part of the question where they got most people got a P. So instead of getting a 3.5 on the question, which might have rounded up to a 4, they got a 3.
Why would you round up instead of rounding down?
Because we just said n has to be greater than. It has to be greater than or equal to this number. Sample size is always pretty much going to round up. Here's the other component, y'all. Okay? Imagine this and forgetting the word true. So a rounding mistake and forgetting the word true would take you on a pre-response question from a 4 to a 3. Or a 3 to a 2. Where you've shown that you know so many things. Is everybody with me? This is why I'm pointing these things out, because there's like tiny little things that can really cost you. Okay? Alright. I'm done. We are going to take some notes on the next part on the block day next week on Tuesday. But you will have some time towards the end to go back over the review. My suggestion to you is that you have the review done when you walk in on Tuesday so you can check it and ask questions. If you wait until, Tuesday to do the review, then you're going to be in trouble in terms of asking questions. Does that make sense? So if I were you guys, on Monday, even though we're not at school, I'd spend a half hour looking through the review. Because you have a quiz on Thursday over that review. Is everybody good? Originally your quiz was going to be on Tuesday. I'm pushing it to Thursday because I thought you'd have more time today to work on that review. And I don't feel comfortable saying, like, here's the review, come back and be ready for the quiz. So me giving you that more time on Tuesday sure would be appropriate for you to take advantage of the more time I'm giving you by having questions ready for me as opposed to starting it on Tuesday. Did you guys catch my drift on that?